Okay, refraction of light. Not reflection, but refraction. Slightly different. Refraction refers to the bending of the path of light. Okay, so we're going to start with a picture that we drew before. Get a little bit thicker. We're going to draw, maybe I'll write here just the bending of light. That's kind of what it means. Okay, so we'll draw this picture. I'll draw this boundary line here. And we're going to put, this line is a boundary between air and water. And I'll use a different color. We have drawn pictures to show that if a light ray comes in like this and hits this boundary, the incident light ray, we've learned already that it reflects off of this boundary, and it reflects in a way that if we draw the normal line here, the reflected ray will bounce off at exactly the same angle that it came in on, right? So we say that this angle right here and this angle are the same. I'll use two thetas to show them. One is the incident incoming angle and one is the reflected angle. Okay? Now, the other thing that happens is that the light, because water and air are both transparent, the light can also go through. So I'm going to take my normal and I'm going to extend it down here like this. So what actually happens is only some of the light reflects, but some of the light goes through into the water. I'll use a different color for that just to highlight it, but it goes through on a different course. It gets bent. Okay? So I'm going to draw it sort of bent like this, going down. See how it's closer to the normal line? It's bent closer. And so what we have down here is another angle that's a different angle from the incident or reflected angles up above. This is a very different angle, the angle of refraction. Now the problem is that reflection and refraction both start with R, so we can't call it theta R. We have to call it something else, right? So, we could call it anything we want. Let's call it theta 2, just so it's different. It's important to realize, though, that it's a different angle than this one up above. And that represents the light that goes down into the water. This is the refracted light. Okay? If this is the, up here, if we have the reflected light ray, then down below we have what's called the refracted light ray. Okay, so what we're going to do is explore this process and figure out what's going on here at the bottom of this picture. Okay, so the first thing we have to do is understand something about light, and I'm going to remind you of a few things that we learned already. And one of them is that light is a wave, right? So we can draw waves like this. It's a wavy, sort of like on the water. And remember that what's waving is something called the electromagnetic field. We talked about this in a previous lesson. And it's like an invisible ocean that surrounds us. And anything that has a charge, if it wiggles, it will make ripples and waves in this invisible ocean that we can detect. Our eyes can detect some of them. Our eyes can detect the ripples and waves that are the right size to make red, orange, yellow, blue, green, blue, and violet light. Our skin can detect the infrared wiggles. And we've developed electronic devices and machinery and things that can detect gamma rays and X-rays and radio waves and so on. So we have to remember when we draw these lines. They represent wiggly waves. Now, what's interesting is what happens when a wave uh, goes from one substance to another. Well, something interesting does happen. It changes the speed at which it goes. So the first thing we're going to talk about is the speed of light rays, just to figure that out. How fast do light rays go? How fast does this wiggle travel through the water? Right? You've all seen, if you look at the top version of a stone dropped in the water, and you've all seen the ripples that go out, right? The little ripply waves. And you've watched that. You throw a stone, and you can see these waves are all going out. And they go fairly slowly. You can watch them go. They're not super fast. Light, however, is extremely fast. The speed at which the light ripples travel depends on what light is in, but what we do is we use the idea of a vacuum, which is a place that has no matter. In a vacuum, the speed of light is very fast. It's 3 times 10 to the 8 meters every second. That's the standard way in physics of using speeds. We use meters and seconds. So 3 times 10 to the 8. Remember your scientific notation. That's this much. Right? That's 300 million meters every second. And if you want to change that into sort of kilometers an hour to give yourself a sort of an idea of what that would be, right? You would have to take 300,000, or 300, sorry, million, 3 times 10 to the 8, and you would have to, first of all, you'd have to change it to kilometers by dividing by 1,000, and then you'd have to change the seconds into hours by multiplying the whole thing by 3,600, and you get a number that is pretty close to 1 billion kilometers an hour. Just so you have an idea. On the highway, you go 100 kilometers an hour. Light rays travel about 1 billion kilometers an hour. That's really, really fast. Now, what's interesting, though, is on Earth, that means that it seems like light goes anywhere as fast, like instantly. But in outer space, where there's long distances, light can take a while. So, for example, the Earth is about 4.5 billion kilometers away from the sun. Or sorry, no, that's not right. It's 150 million, sorry. The Earth is, if this is the sun, and then the Earth is out here, it's 150 million kilometers away. So it doesn't take an hour for the light to go, but it does take a while. It takes about 8 minutes. So when light on the sun travels to the Earth, it makes its ripply way towards the Earth. It takes about 8 minutes before it actually gets here, even going that fast. That's how far away the sun is. And light is considered to be the fastest thing in the universe. So that's pretty cool that it takes a full 8 minutes to get from the sun to the Earth. And of course, if you want to talk about going to nearby stars, which are many, 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 many billions of kilometers away, light could take years to go from one place to another across the universe, which is an interesting thing because that means we're seeing everything sort of back, we're seeing everything delayed. So what's cool is if, let's say you could go to the sun. Obviously you can't, but if you could stand on the sun and wave, it would take 8 minutes before somebody on Earth saw you waving. So anyway, that's how fast light goes through space in a vacuum. But, and that's basically what we call the standard speed of light. Or so we give that a special name. So we call this 3 times 10 to the 8 meters per second. We give it a letter. We call it C. The letter C stands for the speed of light in a vacuum. And it's a very important number because it's involved in a whole lot of physics. The fact that light goes this fast is actually very interesting. But that's because the light is traveling just through the electromagnetic field with nothing in its way. If you put something in its way, like water or glass, then the water or the glass changes how fast the light can ripple. It slows it down. So matter slows down light. But not very much, but enough to notice. Okay? I'm going to put that. I'm going to put not much, still extremely fast, but enough to notice and enough to make something weird happen. So when light enters glass, it goes slower than light going through the air or going through space. When light goes through water, it goes a little bit slower than when it goes through outer space. Let's look at what happens to a wave when it goes from one thing to another. If it slows down, let's look at what would happen. So it's hard to draw waves on a board because how do you draw three-dimensional things, right? So this is easy. But what would happen if you were looking down from the top on this wave? It'd be hard to draw it, right? But what we could do is we could use the little bumps or wave crests. And if we were looking down on it, we could just sort of imagine that, if you're looking at the ocean, these are all the tops of the waves like this. And the wave, of course, is traveling across like that. Does that make sense? Right? We're looking at all these. It's like these are long, drawn-out waves as they roll. Okay? So these are what we call the wave crests. Looking at this picture over here from the top. Okay, so once we get that into our heads, let's see what would happen if we had a boundary between air and water. Okay? Now air is very close to a vacuum. It's there, but it doesn't slow down light as much. So light goes very fast in air, but it goes slower in water. So I'm just going to write that here on the picture. The speed of light here is faster in the air and slower in the water. Let's draw our waves. Let me draw this wave coming in, okay? And I'm going to draw the wave crests like this. I'll draw them nice long wave crests coming in. Da-de-da, and they're moving towards the surface like this. And they're all going the same speed. So all these lines are all moving sort of this way. There's how we would have drawn my little arrow, right? They're all moving. But look what happens here. The tip of this line is dipping into the water now, isn't it? But it's going to go slower once it's in the water. So the black part of the line I just drew is going to keep going the same speed, but the little part here that's sort of dangling in the water is going to slow down. It's going to lag behind a little bit. And if I keep drawing all these waves like this, or whoops, that's supposed to be black. All these crests. Undo. If I keep drawing these, we'll see an interesting thing that happens. Let's draw these continuing down. More and more of them are going to dip into the water, right? Now let's draw the little dippy parts. But the parts that are dipping into the water are slowing down, so they're sort of lagging behind like this, you see? They're not keeping up. They're lagging behind. And if we keep drawing this picture, if I keep going as much as I can, we eventually get to a point where the entire wave is now dipped into the water, but it's lagged behind. This wave is going this way. See how it's bent? The lagging behind causes the wave to bend. I also see here that I'm going to fix the picture on top. I see that my top has, I've been going down. I shouldn't have. This should all be a nice straight line. That's better. Okay? So you can see there's an angle here. If I use green, well, this is the direction the light was going before, but now it's sort of bent a little bit through this angle, and it's going in a different direction. And this is called refraction, this bending process of light. And it only happens when light goes from one substance to another. Now, of course, the substances have to be somewhat transparent or even translucent for this to happen. Because if it's an object that's opaque, like bouncing off a desk, no light can go down into the desk. All the light gets reflected or absorbed by the desk. But in the case of transparent media like these, transparent things, the light can change. So I hope that picture gives you an idea of what refraction is. It's kind of like the same thing that happens if you've ever been in a car. Some of you are too young to drive, but if you've ever been driving a car, on the side of the road, here's the road, and on the side of the road is all this gravel, the shoulder, right? There's the gravel. If you're driving along the road and you're falling asleep or you're not paying attention, and one of your wheels, let's say here's the car wheels, here's my four wheels of my car, I'm driving along. But if I veer over a little bit so that one of my wheels grabs the shoulder, so these two wheels now are in the dirt. The dirt slows down those wheels because it's not as smooth as the pavement. So what happens is the two wheels on this side keep going in the straight direction, or at least they want to. But the two wheels here are lagging behind, just like the lagging behind waves right here. They were lagging a little bit. So what that means is that the right half of the car is going to go a little slower than the left, which means the car is going to go and bend. It's going to get pulled over into the dirt. And if you've ever driven a car, or even if you've driven a four-wheeler or something and you hit some mud or something that's different than the road you're on, it pulls, right? Pulls the car because it slows down the right side of the car. So here, the bottom part of these waves right here, all these little hanger bits that are in the water are being slowed down, which pulls the whole wave a little bit down like that. Now, if you went the opposite way, what would happen is this. Let's draw an opposite way really quick. Let's draw a different boundary. Let's say that you were light that was traveling in water, but then under the water there was a piece of glass and the light went into the glass. Actually, no, I got that backwards. Sorry, my mistake. Let's say that, well, how about light that was underwater, right? And then it was going out into the air. What if it was upside down? Well, let's draw the light waves. If we do the same thing, what would happen if my waves are coming in like this? Now, here's what's interesting. What happens to the little dippy parts in the air? Well, what's interesting now is the light is slower in the water and it's faster in the air. So that means the dippy parts aren't going to lag behind. They're going to actually start to go faster. The little bits, the little ends are going to speed up and they're going to be able to go faster, so they're going to get ahead of. That's not a very good, let me redo that. They're going to start to go ahead of the other waves, just a little bit. Boy, there, okay, I think we got it now. Something like this. So that when the light rays finally get into the water or the air, look at what happens. The right side has sort of gone faster. This side was going in like this along this way. But the red side has sort of bent. But it's bent the other way this time. Instead of bending down, it's bent out the other way. Right? There's a different angle here. So what we can learn from this is a very important rule about how light refracts. And that rule is this. If the light is passing from a a slower to a faster substance. And there's a word we use for that. We think about the density of the substance, right? What we call the optical density, which is a measure of how much it slows down or the light that it travels through. So if you pass from low optical density to higher density, that was the situation we had where we had air, which is lower, and water, which is higher. What happens is you bend. Let me just draw it again. There's my light ray coming in. I'm going to put the arrow up here. I'm going to draw the normal line, because remember how we always use that normal line, the perpendicular line to the boundary. What happens is you bend in a way that you go closer to the normal. Okay? Here's the line that you were on. That's the way you were going before. But you'll notice what's happened is the green line has been bent this way towards the normal. So the ray bends toward the normal when you go from low density to high density. And that's because in the water, the high density, the wave bits get slowed down and they drag behind, which drags down the wave to a different direction that's closer to the normal. But the opposite is true when you go from a high density to a low density. I'll just pause for a minute. So some people were catching up. So now we can move on to the next, which would be another picture. And this would be the opposite. And it could be anything. I used air, I used water. We could have light that was inside of glass, a piece of glass, and was going out of the glass into the air. Right? Doesn't matter. And of course, in this case, the glass is the slower one, and the air is the faster speed. So what happens here in this case is when the light ray comes in, like that, if we draw our normal line, we saw from the picture before that it tends to bend sort of this way. It went faster and therefore bent the opposite way. Here's the line that the light was going on before, and you can see that it has bent this way, which means it's bent away from the normal line. So we say that when you go from, so we should write this, I guess. If the light is passing from high density to lower density, like it is here, to lower density, the ray bends away from the normal. Okay, so I'm just going to jump back up here. Here's the first picture. When you go from low density to higher density, the ray bends towards the normal. You can see it in the picture, bending sort of closer to the black dotted line. But then when you do it the other way, the ray bends the other way, passing from high to low. The ray bends away from the normal. Okay, so now, how do we figure out what's faster and what's slower? That's kind of the next step. If we know what the light is going to do, we kind of have to know which things are faster and which things are slower. How would we know, right? Is light faster in glass than it is in water? Or is it slower? I don't know. What if you passed light through a solution of alcohol? Is that fast or slow? Hard to say. So what we need to do is we need to find a way to determine how fast things go. So the speed of light in matter going through substances is described by something we call the index of refraction. The index of refraction, and we use a little symbol n for the index of refraction. Now, what exactly is it? Well, it's a comparison. So what we do is we take, let me get a finer pen here. What we do is we say that n, which is the index of refraction, is a comparison of two things. Now remember, in mathematics, compared to is translated into division. When we do divisions or fractions in mathematics, that's how we do comparing, right? That's how comparing works. So we're going to create a fraction. And on top of the fraction, we're going to have the speed of light in a vacuum. And then we're going to compare that to the speed of light in the matter. And we're going to use shortcuts for these long sentences. We're going to call the top of this what we called it before, remember? C, the speed of light in the vacuum. And then in physics, we often use a little v for speed because it's like velocity, right? V. So the speed of light in the matter is going to be called v. So this shortens to a much simpler little expression, n equals c compared to v. But you have to remember what those little c's and v's stand for. Okay. Now, if we do this comparison, we can calculate n. If we measure how fast light goes in different things, we could fill in the numbers and we could get n's figured out for all kinds of things like water and glass and air and all those such things. It's a little bit complicated to measure these speeds, and we're not going to get into the details, but what I can show you is that there are some common substances that light goes through, and what we do is we find charts, or we make up charts that have different indices of refraction or indexes of refraction. Okay, so let me show you a couple of those. If we try to figure out n's using this relationship, if we compare, let's take a vacuum. Whoops. Well, in a vacuum, obviously, it's going to be a value of 1, right? So in a vacuum, you're going to have n equals c over v. But the speed of light in a vacuum compared to the speed of light in a vacuum, right, is the same thing. So we say that equals 1. The index of refraction for a vacuum is 1. But if we do something like air, let me get a thinner pen here, and we do n equals c over v for air, what we find is the top part, the c, that's like 3 times 10 to the 8, remember, meters per second. And we find that the bottom is just a wee bit slower. A very small bit. Okay? So I'm just going to write here a wee bit slower, because we don't really need to worry about the number. But what happens to a fraction if the bottom is a little bit smaller than the top? Well, it begins to get bigger, right? It goes bigger than 1. Watch. Here's a fraction, 2 over 2. Well, that's exactly the same as 1. But if I make the bottom a little wee bit smaller and make it 1.6, well, if you divide 2 by 1.6, you're going to get a number bigger than 1, right? You're going to get 1.25. So when we start putting things here that are a wee bit slower on the bottom, like air or glass, we start to see the number go up. So the bigger the number, the slower the light goes, right? So for air, the index of refraction, because it's only a wee bit slower, it's not much different. According to this book, it has a value of 1.00029. Well, that's so bloody small, it's not even worth worrying about. It looks like air is pretty much the same as a vacuum in terms of the speed of light, right? Light goes through the air almost at exactly the same speed as it does going through a vacuum. But if we take another object, let's take water. And we go n equals c over v. That means it's 3 times 10 to the 8. But this time, it's not a wee bit slower. It's a fair amount slower. Fair amount slower. And when you put the numbers in and you do the math, this comes out to 1.33. 3333, actually. I think it's a repeated, but 1.3 is good enough for us. We'll just use 1.3. Well, that's a significant difference. That means that that water is quite a bit slower, or the speed of light in water, I should say, is quite a bit slower than the speed of light in air or in a vacuum. And then if we continue, there's all kinds of substances. Let's look at glass. Now, the problem with glass is there's different kinds of glass. There's what we call crown glass, which is kind of like the normal kind of glass that we're mostly used to. So if I, whoops, let me go back here. Crown glass. That's kind of typical glass. If we do this, right, n equals c over v. So we compare the speed of light in a vacuum to the speed of light in the glass. We get this. I'm not going to keep writing the other things. We get, apparently, according to the chart, 1.52. Well, I guess I'm going to put my 3 back up here. We're going to do everything with 2 decimals. I guess that'll make it even, okay? We'll use 2 decimal places. But you may also have at home crystal glass, which is a little different kind of glass. So crystal glass. Your mom might have some fancy wine glasses or something that are more expensive, right? And if you break the crystal glasses, you get into a lot of trouble because they cost more. Crystal glasses actually slow down the air a wee bit more. The n is 1.54. But it's safe to say if you use 1.5-ish for glass, that's reasonable, right? What other things might we pass light through? Well, one of the most densest things, one of the most slowest things that light can go through, that's kind of like a naturally occurring common substance, is a diamond. Light goes through diamonds and it makes wonderful little colors as it bounces and reflects inside. But believe it or not, it's so slow. This comes out to 2.42. That's very slow. It slows down 2.5 times. It's 2.5 times slower than light in a vacuum. So that's half speed, right? But half of 1 billion kilometers an hour is still 500 million kilometers an hour, so it's still pretty darn fast. So you can look up a chart that tells you all the different n's. In your textbook on page 454, you'll find a chart that has all the n's that you will need listed there. Or you can Google indices. If you just Google, the plural of index is indices, so indices of refraction. And if you Google that, you can get all kinds of tables and lists that have been calculated to figure out the n's for any substance you want. And then that will allow us then to start doing some interesting mathematical things to figure out what those angles were when it comes time for the light to bend. Okay? So in our next video, we'll talk about how we calculate the bending of light. But for now, this is just the main idea. Okay? All right, so we'll stop there.